are almost there. It's episode 6. Let's go.
Yeah, guys, so we're saving the best for the last, episode 7. Oh boy, you have to check it out. Let's dive in on to the next. So just pause the video like we always do. Check out the problem. If you have difficulties, check out what I've done. Let's go. So we have figure 4 below shows a 1200 microfarad capacitor in series with a lamp of power rating that and a power supply of frequency that and a switch. Determine the root mean square voltage to light up the lamp to its full brightness. Okay, so of course we have the voltage reading of the lamp, the current reading, and so we can get the resistance of the lamp, right? We can also get the reactance of the capacitor, of course 1/2 pi Fc. 2 pi there, Fc is capacitance, and you put all those things, you get the reactance of the capacitor to be 2.65 ohms. Now you can get the total impedance in the circuit by simply getting, of course, square root of R squared plus Xc squared, and that gives us this, which is 10.34 ohms. Now the root mean square voltage, of course, is I times Z, and our I there is 0.25 as the current in the circuit, multiplied by Z, which gives us 2.6 volts. Now the Roman 2 is asking for us to get the potential difference across the capacitor and the lamp. Well, VC is basically I times XC, right? Ohm's law, really. Okay, Charles law, really. So VC is 0.25 times 2.65, right? Because our current is 0.25, our XC is 2.65. We calculated it here, 0.66 volts. We can get the voltage now across the resistor. It's of course 2.5 volts. Remember, we don't have to worry about that. So Roman 3 says verify whether the sum of the PD across the capacitor and the lamp is equal to the root mean square supply voltage and comment on the result. Well, in AC circuits, we sum voltages by, of course, using the Pythagorean theorem. Okay, so VC squared plus VR squared gives us this, and so that's 2.6 volts, which is equal to what? The root mean square voltage. And so you realize that the voltage across both is equal to the root mean square voltage. That is it, guys. That is it about the AC circuit part. Let's move on to the next. Hope you enjoyed this part, right? So the part B is on waves. Again, just go ahead and try the problem out and then check out what we've done. So differentiate between interference and diffraction of light. That's easy peasy, lemon squeezy. Interference is the superposition of similar waves in a medium of wave propagation, right? So as long as those waves are superposing, then that's interference. While diffraction is the spreading of waves when they go through an aperture, okay? So that one is easy. So this says power beam of light of wavelength that in air is incident on the slit of Young's double slit experiment. A thin film transparent plastic of refractive index 1.48 and thickness that is placed over one of the slits. Determine the increase in optical path difference of the light passing through the thin film. And okay, so the path difference, of course, n minus 1 times t. Okay, that's the equation. So n here is the refractive index of the material you're putting on one of the slits, minus 1 multiplied by the thickness, and the thickness is 5.2 times 10 to the negative 6 meters. So if you do multiply this out, you have the path difference to be 2.5 times 10 to the negative 6 meters. Okay, so we can go on and then say, all right, how do we, remember the examiner is asking you now to calculate, hence determine the number of fringes by which the central fringe is displaced. Okay, so that path difference, of course, equals to m lambda, all right? So a particular ordered bright fringe M now is formed as a result of this extra path difference. So what's the order there? M would be dx on lambda. So get dx divided by lambda. The wavelength of the light is 5.5 times 10 to the negative 7. So we get 4.5. So that tells you that, well, the central fringe gets displaced through 4 fringes. Okay, fringes, remember M is an integer, so 4.5 is not an integer. You should know that. Good. So this guy is displaced through 4 fringes, and you don't round up, you always round down. Okay, so it tells you that there are only 4 possible bright fringes that are possible to be observed on that. 4.5 really means that, hey, I could have gotten to the 5th, but I don't have it on the screen. Okay, so I have only 4 bright fringes on the screen, so that's why it has to be displaced through 4 bright fringes right there. So Roman 3 says explain how the fringe spacing will change if, okay, the slit separation were increased. What do you know? You know the formula, x equals lambda d on A. X is of course my fringe separation right there. So notice that if I'm increasing the slit separation A, yeah, this is my slit separation down here. that does what? That decreases the fringe separation x. So my fringe separation decreases on increase of the slit separation. Are we there? So yeah, you've told the examiner what happens if you increase the slit separation right there. Now the slit screen distance will increase. If I increase the slit screen distance, which is this capital D, what happens? Notice that the fringe separation just directly increases since they have a direct relationship here. So increasing slit screen distance, capital D, increases the fringe separation X. Okay, and that's it. That's it, guys. Let's go over to C part. So again, this is a C part. It's an interesting problem on projectiles. Pause it, check it out, and see what we've done. So a spaceship is transporting and distributing aid to refugee camps. It's traveling horizontally at the speed of that, at an altitude of that. It releases a parcel when it is directly above a point X on the level ground to a nearby camp. Calculate the time of flight of the parcel. Okay, that's an easy problem. So this is our projection, right? So you're releasing the particle at the point X here. Okay, so because you're traveling horizontally, that particle has an initial horizontal impulse on it. And so the initial horizontal velocity will just be the velocity which the system was traveling with. That's why you see this my u meters per second here. Okay, so the vertical distance here is 300 meters. We get this diagram marked down, and so you notice that uy is 0. So the initial vertical component of the velocity is 0 right here. Okay, so my ux is this, and so I can use equation of motion sy to calculate this vertical displacement. Be sy. Uy times t, remember my uy is 0 plus half gt squared, right? So that would be my time of flight there. So you notice that, hey, if I want to get now this time, since this guy is 0, I'll simply make c the subject. I have 2 sy divided by g square root of that. Okay, so my time of flight there will be square root of 2 sy. What's my sy? It's 300 meters divided by my g, of course. I get 7.8 seconds for my time of flight. Now I can go over and then talk about the speed of impact of the parcel on the ground. So Vx is equals to Ux is equals to 50 meters per second. So what does this really mean? It means that the horizontal component of the velocity, you see this initial horizontal velocity is 50 meters per second. It's never going to change. Even when the particle strikes the ground here, the horizontal component of the velocity will always be what? Will always be this Ux. So that's why I say you see me writing Vx equals Ux, which is 50 meters per second. And why does it not change? Hey, because there's no acceleration in the horizontal direction. Okay, so the particle stays in a constant speed in that direction. All right, so my Vy is of course Uy plus half g plus gt. Okay, that's from equation of motion V equals U plus at. And so you notice that my Vy, since Uy is 0, my Vy is gt. And so my Vy is this, and so I put in those things, and so my Vy is 76.68 meters per second. Now what's my V? My V is square root of Vx squared plus Vy squared. And so my V is square root of Vx, which is this, and my Vy, which is this. So get square root, you have 92 meters per second. And so the third Roman 3 part. Okay, so again, we want to calculate the distance of the cam from X if the parcel did not miss its target. Okay, so my X there is Ux times T, right? All right, so you notice that of course my ux there is 50 meters per second, my time there is 7.8, and so my x horizontal distance covered by the parcel would be 390 meters. And that's it, guys. So let's move over to the last episode of this mock.